Hello friends, so welcome to my channel Dr. Sunirban's Chemistry School. In this video, we will focus on organometallic reactions and catalysis. As the subject is quite broad, so we'll divide in few parts and gradually we'll discuss the entire part. So to get the knowledge about the entire organometallic reactions and catalysis, please follow the subsequent videos. Before we go or talk about the reactions, we'll take a brief look about the organometallic chemistry. Although the details of organometallic chemistry has been already given in video related to basics organic chemistry. Now organometallic chemistry basically is nothing but a bridge between organic and inorganic. So in this organometallic chemistry, the complexes which have at least one metal carbon bond will consider as an organometallic chemistry. The most of the ligands which are associated with organometallic complexes are mostly pi acidic type, and the sigma bonding or metal carbon bonds sometimes are sigma type, sometimes pi type, depending upon the availability of the valence electrons in the donor ligands. So usual ligands are like carbonyls, alkyls, pi electrons in alkenes, even extended aromatic components. Now when we are talking about the organometallic reactions, basically we can categorize the entire reactions in two categories. Reactions involving gain or loss of the ligand. That means coordination number or sphere is going to change through the reactions. And the second one, where coordination number is not changing, but a subsequent modifications of the ligands is taken place. But the modification is ligands only we consider in these organometallic reactions where the metal ligand bonds association and dissociation takes place. Now when we compare the different reactions involving gain or loss of ligands, for example through dissociation, the coordination number decreases. Substitution, that means one substituent gets substituted by other one, so the coordination number remains unchanged. Addition means increases basically. And all these three reactions ultimately does not change the formal oxidation state of the metal. Metal remains its same oxidation state. However, in oxidative addition, which also involves the increase of coordination number, it also increases the formal oxidation state. That means it oxidizes the metal center. So electron transferred from metal to the ligand. And exactly the opposite reactions, what is known as reductive elimination. Elimination means decreases. So ligands are get eliminated from the metal center. And reductive means the metal center get reduced. So formal oxidation state decreases. Now we'll come one by one. The dissociation and substitution in organometallic complexes are very much similar like the reaction mechanism we have studied for coordination chemistry. One or more ligands can be dissociated and the incoming ligand can be substituted on the dissociated position. So during the dissociation, vacant coordination sites will be opened, and for the stability of the overall complexes, it can reflect in two ways. Either it will undergo a rearrangement, like in this case the metal-metal bond has been formed to overcome the electron deficiency due to the removal of carbonyl, and in this case removal of carbonyl followed by the substitution of phosphine ligands. Particularly substitutions are very important in case of coordination organometallic catalysis reactions. But substitution reactions are always not follow a similar mechanistic pathway. some of the dissociation reactions or substitution reactions where the main path of or main mechanism of the reactions involve the dissociation. For example, in nickel complexes of this kind, which is 18 electron system, undergo a dissociation followed by substitution. But main rate determining steps is the dissociative pathway, and that's what the overall rate is unimolecular. However, there are some complexes like, for example, molybdenum hexacarbonyl complex, which is although saturated, looks like the dissociative pathway will be favored here. But the overall rate of the reactions shows that it's a combination of unimolecular as well as bimolecular pathway. So unimolecular means definitely it's a dissociative pathway like this one. But the bimolecular gives a indication of association. But obviously, truly SN2 type reactions is very difficult because it's coordinately saturated. And therefore, as we learn from the coordination chemistry, kinetics, reactions, mechanism, a association could be possible. And during this association, which is the activated step, where the both metal complexes and ligands are involved, and therefore the kinetics will follow the bimolecular. On contrary, the dissociation of phosphine, these are also very important part in various organometallic reactions, can be very easily described or perfectly described through the Coleman's cone angle. In case of the phosphine complexes particularly, the steric crowding is overruled over the electronic factor because phosphine have tri-substituted components which have a large space occupancies, and its large occupancies or bulkiness can be described through cone angle. So larger the cone angle means bulkier the substituent or ligands. So if I consider a substitution like reactions like this, where the two phosphines are cis to each other, since they are cis, so steric factors will obviously dominate. And if we try to substitute one of the phosphines with a very small carbonyl, the rate of the reactions definitely will be depends upon the phosphines dissociation. And the dissociation will be phosphines totally depends upon the crowdiness or bulkiness of the phosphines, and that reflected through its cone angle. For example, in this case, if we take these kinds of phosphine ligands where the two substituents are methyl smaller, and gradually if we increase the bulkiness of the substitution, that will reflect on its gradually increasing in cone angle. And obviously, as expected, what we'll find, the rate of the reactions increases with the increase of bulkiness or cone angle. And if you find that the most bulkiest one in this example shows almost fourth order increase in its substitution reaction. That means the phosphine lost very fast in case of the bulky one. And the phosphines dissociation is sometimes very major or important steps involved in many catalytic reactions. Now, if I just briefly look at the importance of this phosphine as a co-ligand in different organometallic complexes in different catalytic processes, the larger cone angle of bulky phosphines make the dissociation much more easy. So when the catalysis proceed, the catalyst can easily open a vacant coordination site through the easy dissociation of phosphine, leading to the association of the reagents to the metal center. Secondly, the bulkiness of the phosphine makes the metal center some extent coordinatively unsaturated or as well as electronically, because more bulky ligands will not allow the saturation of the coordination sphere, and therefore electronically as well as coordinatively metal remains unsaturated, leading to the probability of association. And the third one, They increase the selectivity for a smaller ligand addition on a sterically crowded metal center. That means more phosphine ligands on the metal center please allow only the smaller ligand to approach and binds with the metal center rather than the bulkier one, right? So this is one of the very important advantage utilizing the phosphine ligands in organometallic complexes. Now coming to another important reactions categories which are also associated with the loss of ligands. As we know, the nucleophilic substitution reactions from our organic chemistry background, that a nucleophile easily substitute another nucleophile, and these reactions we are very much well known about the nucleophilic substitution reactions. We are not going to talk about the mechanistic pathway. It could be unimolecular or bimolecular. But the nucleophilic substitution basically involve a nucleophile will substitute another nucleophile. Sometimes there are many anionic organometallic complexes also shows a similar type of reactions where this organometallic anionic complex acts as a nucleophile to displace another nucleophile from an organic compound and attach this organic component, or basically we can say activate these organic components. And that's what this kind of complexes utilized for several type of organic synthesis. Some of those are very important in terms of their nature. Let's take an example. This iron complexes shows a very good catalytic activity to generate different organic components through the nucleophilic displacement pathway. This complex, when allowed to react with alkyl halide or acyl halide, it replaces the nucleophiles X group and include the alkyl or acyl group within that one. So this step is basically the nucleophilic displacement, which subsequently reacting with different substituent gives a different varieties of organic components which are in general sometimes very difficult to produce through the normal organic synthesis. So not only these exceptional reactions, but there are many organometallic anionic complexes which has been utilized for the preparation or synthesis of many important and valuable organic components through nucleophilic displacement reactions. Let's few of them like chromium tetracarbonyl complexes or cobalt complexes or molybdenum complexes. There are a wide variety of complexes are associated. However, our most important goal is to understand the catalytic pathway of different catalysts involved. Once we know the catalytic pathways or mechanism involved in a catalysis process, then we can easily tune to get various product. Let's take an example of Wilkinson catalysis, which is basically a rhodium triphosphine complex, which upon binding with alkene, it easily hydrogenated. That means the Wilkinson catalysis utilized for the hydrogenation of alkene. The basic pathway or basic mechanistic pathway follows several steps, which are at the beginning is the dissociation of phosphine. As I mentioned in the earlier, the phosphine plays a very vital role for activating the catalyst. However, that activated catalyst follows several pathways which are involved oxidative addition, migrative insertion, reductive eliminations. So these are some of the very vital and obviously very unique reactions involved in organometallic complexes. In our next video, we'll mainly focus on these unique reactions involving organometallic complexes. So thank you for observing my videos, and if you like it, please subscribe my channel and also don't forget to press bell icon to get updated about the videos. And if you have any suggestions or any queries, please don't hesitate to mail me. Thank you.